Welcome to EducAgent Studio, where a crew of AI agents help us teach, and you learn with ease. Here's the problem we'll solve today. Here are the three given vectors, each shown as a column vector in R2. We will compute u.v, u.w, u.v plus w, and w.v using the standard formula for the dot product. If you don't know the solution yet, you'll experience the satisfaction of learning it soon. Pause and think for a moment if you like. First, let's compute u.v. Recall the dot product formula. Multiply corresponding components and add. Compute the products. Negative 0.6 times 4 gives negative 2.4, and 0.8 times 3 gives positive 2.4, which sum to 0. Next, let's find u.w. Multiply components and add. Negative 0.6 plus 1.6 equals 1. So u.w equals 1. Now compute the sum v plus w. First add v and w component-wise to get the vector 5, 5. Compute directly. Negative 0.6 times 5 plus 0.8 times 5 is 1. This matches distributivity. u.v plus u.w equals 0 plus 1, also 1. Finally, let's compute w.v. Multiply and add components to get 10. By commutativity of the dot product, w.v equals v.w. Let's recap the results. First two results, u.v is 0, u.w is 1, and the sum is 1, while w.v is 10. Great job! Watch the next video to learn more. It's fun and slightly addictive, like solving tiny puzzles with numbers. Welcome to EducAgent Studio, where a crew of AI agents help us teach, and you learn with ease. Here's the problem we'll solve today. We treat v and w as column vectors in Rn with components v1 through vn and w1 through wn. The tasks: find unit vectors in the directions of v and w, compute the cosine of the angle between them, and pick vectors a, b, c that make angles of 0, 90, and 180 degrees with w. Take a moment. Can you guess how to get unit vectors and the cosine from dot products and norms? If not, you'll enjoy discovering it now. First, we remind ourselves how to compute lengths or norms of vectors. A norm of a vector is the square root of its dot product with itself. This gives the lengths of v and w. Note, to form unit direction vectors, we require v and w to be non-zero. Next, we form unit vectors by dividing each vector by its norm. Here v hat and w hat are the vectors v and w scaled to have length 1. Divide each column vector by its norm. If either original vector is the 0 vector, a unit direction is not defined for that vector. Now we connect the dot product to the angle between vectors. The dot product equals the product of lengths times the cosine of the angle between them. Therefore, cos theta is the dot product divided by the product of the norms, provided neither vector is 0. Finally, we pick explicit vectors a, b, and c that make the requested angles with w. For 0 degrees, choose any positive multiple of w. A simple choice is a equals w. For 180 degrees, choose a negative multiple, c equals minus w works. For a 90-degree example in R2, take b equal to the column vector bracket minus w2, w1, n bracket. This vector is orthogonal to w. Take B equals negative W2, W1. Computing the dot product gives B dot W equals minus W2 times W1 plus W1 times W2 equals 0. So B is orthogonal to W and the angle between them is 90 degrees. In higher dimensions, set 2 coordinates to the perpendicular pair and the rest to 0, or choose any non-zero vector whose dot with W is 0. Let's summarize the key formulas and choices. Unit vectors divide each vector by its length to get V hat and W hat. Cosine of the angle, dot product over product of norms. Choices A equals W for 0 degrees, C equals minus W for 180 degrees, and B, any non-zero vector orthogonal to W for 90 degrees. Nice work! Watch the next video to learn more. We'll pick specific V and W and compute numbers in the next lesson. See you there! Welcome to EducAgent Studio, where a crew of AI agents help us teach and you learn with ease. Here's the problem we'll solve today. We'll use the dot product formula. The cosine of the angle equals the dot product divided by the product of the norms. Here are the 4 vector pairs we'll analyze. Each vector is shown as a column vector. Find theta for each pair, compute the dot product, the norms, then cos theta, and finally the angle. Pause now if you want to think about any case. If you don't know the answer yet, you'll soon experience the satisfaction of learning it. Part A, 2-dimensional vectors. Compute dot product and norms directly. The cosine simplifies to 1/2, so the angle is 60 degrees. The picture confirms the computed result. The 2 vectors meet at an acute angle of 60 degrees. Part B, a 3-dimensional example. The dot product is 0, so the vectors are orthogonal and the angle between them is 90 degrees. Because the dot product is 0, these 2 vectors are orthogonal and the angle between them is 90 degrees. Part C, 2 vectors with similar length. The dot product and norms give cosine 1/2 again, so the angle is 60 degrees. Again, we obtain an acute angle of 60 degrees between the 2 vectors. Part D, an obtuse angle case. A negative dot product yields a negative cosine. After simplifying, we get minus root 2 over 2, giving an angle of 135 degrees. Because the dot product is negative, the cosine is negative, and the angle between the vectors is obtuse, 135 degrees. Let's recap the results for each pair. Here are the 4 results side by side. A and C are 60 degrees, B is 90 degrees, and D is 135 degrees. Great work following along. Watch the next video to learn more and see these ideas and other examples. It's a fun ride. Welcome to EducAgent Studio, where a crew of AI agents help us teach, and you learn with ease. Here's the problem we'll solve today. Here is the fixed vector n, written as a column vector. We want vectors perpendicular to this one. Any vector orthogonal to n must satisfy this linear equation. Our task is to find 3 non-zero vectors, u, v, and w, that are perpendicular to n and perpendicular to each other. Pause and think about whether you can find simple choices. If you don't know yet, you'll get the satisfying answer in the next steps. We'll start with an easy vector in the subspace. A simple choice is u with entries 1, -1, then 2 zeros. It's clearly in the plane x plus y plus z plus t equals 0. Compute the dot product to verify u is perpendicular to n. Next, we seek v orthogonal to both n and our chosen u. Assume v has the form a, b, 0. This choice makes v automatically orthogonal to u, because the first two entries cancel when dotted with u. Impose orthogonality with n to get 2a plus b equals 0, so b equals minus 2a. Pick a equals 1 to get a concrete v. It is perpendicular to n and to u. Finally, we find w that is orthogonal to n, u, and v. Let w have unknown entries p, q, r, s. Orthogonality with u gives p minus q equals 0. With v gives p plus q minus 2r equals 0. With n gives p plus q plus r plus s equals 0. Solve these in order. Solving yields p equals q equals r and s equals minus 3p. Choosing p equals 1 gives this w. Let's check all the orthogonality claims with dot products. U is perpendicular to n. U and v are orthogonal. V is perpendicular to n. V and w are orthogonal. W is perpendicular to n. U and w are orthogonal. All checks pass. A quick recap of what we constructed. One valid choice is u equals 1, minus 1, 0, 0. V equals 1, 1, minus 2, 0. And w equals 1, 1, 1, minus 3. Each is non-zero, orthogonal to n, and pairwise orthogonal. They span the three-dimensional subspace perpendicular to n. Nice work following along. Watch the next video to learn more tricks for building orthogonal sets and orthonormal bases. It'll be fun and a little bit silly. Welcome to EducAgent Studio, where a crew of AI agents help us teach and you learn with ease. Here's the problem we'll solve today. We are given three numbers whose sum is 0 and two vectors v and w formed by permuting the entries. Art A asks for the angle between v and w using the standard cosine formula from linear algebra. Part B challenges us to explain why the dot product ratio is always minus 1/2. Pause and think. Can you see a symmetry or algebraic identity that forces this value? Compute the dot product by multiplying corresponding entries and summing. Because addition is commutative, we can rewrite the sum as xy plus yz plus zx. Keep this expression in mind. The next step links it to the sum 0 condition. Square the sum x plus y plus z. Since the sum is 0, the square is 0, and expansion gives a relation between the pairwise products and the squares. Solving for the pairwise sum gives minus 1/2 of the sum of squares. This is the key identity. Substituting into our dot product expression yields this compact formula for v dot w. Because w is a permutation of v, their squared norms are equal. Both equal the sum of squares, so the norms match. Forming the cosine cancels the common norm factors, leaving a constant minus 1/2, independent of the particular non-zero triple. This illustration uses a representative pair of vectors that satisfy x plus y plus z equals 0. Those two vectors meet at an angle of 120 degrees, which corresponds to cosine equal to minus 1/2. Quick recap of what we learned. For part A, the cosine is minus 1/2, so the angle is 120 degrees, or 2 pi over 3 radians. For part B, the algebra shows the dot product equals -1/2 the sum of squares, and identical norms cancel, producing the constant -1/2 for any non-zero triple summing to 0. If that was satisfying, stick around. In the next video, we'll explore other elegant identities that force fixed angles between vectors. Watch the next video to learn more.